the accidental reaction that changed modern life. It began as a mistake, a reaction nobody was searching for, in a moment that felt ordinary. And yet, the world you live in now exists because of it. To understand why chemistry matters today, we have to forget the idea of tidy equations and lab coats. Chemistry is not distant or abstract. It is a quiet force shaping food, medicine, energy, and even survival itself. Every modern convenience traces back to reactions once misunderstood, ignored, or discovered by accident. And the same pattern continues today, repeating in ways we rarely notice. At its core, chemistry is the study of change. Not dramatic explosions, but subtle rearrangements. Atoms shifting partners, bonds breaking, then forming again. These invisible events decide whether a substance heals or harms, fuels progress or destroys ecosystems. The modern world is built on reactions most people never think about. At first, early chemists believed nature followed strict, predictable rules. If you followed the recipe, you got the result. But reality refused to cooperate. Experiments produced surprises. Colors changed unexpectedly. Substances behaved in ways no theory could explain. What looked like failure often became discovery. One such moment happened when a simple experiment went wrong. A mixture left unattended. Heat applied too long. A container sealed when it should have been open. Instead of ruining the work, the reaction created something entirely new, stronger, more stable, more useful than anything planned. At first, it seemed like a curiosity, an odd material with unusual properties. But then questions followed. Why did it behave this way? Why didn't it break down? Why did it interact differently with air, water, and heat? Each answer led to deeper mysteries. This was the beginning of a shift. Chemistry stopped being about copying nature and started becoming a tool to reshape it. Reactions were no longer just observed. They were guided, controlled, scaled, and once that door opened, it never closed again. What began as a small accident quietly rewired industry, medicine, and daily life. And most people never learned its name. The discovery didn't announce itself with applause or headlines. In fact, many dismissed it at first. It didn't fit existing models, and it challenged what chemists believed materials could do. But quietly, the reaction kept proving itself useful. As experiments continued, patterns emerged. The substance resisted decay. It endured heat that destroyed others. It could be shaped, stretched, and combined in ways previously impossible. What seemed like a laboratory anomaly slowly revealed a new category of matter altogether. This changed how chemists thought about reactions. Until then, most chemistry focused on purity and precision, exact ratios, control conditions, predictable outcomes. But this reaction showed that imperfection could be powerful, that uncontrolled variables sometimes unlocked entirely new behaviors. Soon, similar reactions appeared elsewhere. Different labs, different materials, same underlying principle. Molecules could be persuaded into long chains, forming structures nature rarely produced on its own. These chains gave materials memory, flexibility, and strength. Industries took notice, not because they understood the chemistry fully, but because the results were undeniable. Products lasted longer. Manufacturing became cheaper. Objects became lighter yet stronger. The reaction scaled effortlessly from beakers to factories. However, with scale came consequences. These new materials did not behave like anything before them. They didn't rot. They didn't dissolve easily. They lingered. At first, this permanence was celebrated. Durability meant progress. Stability meant success. But then questions surfaced. What happens when a reaction creates something that never truly goes away? What happens when chemistry outpaces understanding? The same process that solved countless problems was quietly creating a new kind of challenge. Chemistry had crossed a threshold. It was no longer just explaining the world. It was rewriting it. And the long-term cost of that rewrite had barely begun to reveal itself. As production accelerated, the world filled with the results of that single reaction. Streets, homes, hospitals, and oceans slowly absorbed its presence. What began as a solution quietly became a dependency. Chemists understood the bonds they were creating, but not the scale of their impact. These long molecular chains were remarkably resistant. Sunlight barely weakened them. Water passed over them without effect. Microorganisms, which normally recycle matter, could not break them apart. The reaction had produced permanence in a world built on cycles. At first, the benefits drowned out the warnings. Medical tools became safer and more sterile. Food lasted longer. Transportation grew lighter and more efficient. Entire industries reorganized around this chemistry. Economies adjusted. Lifestyles changed. There was no turning back. But the conflict emerged slowly, not in laboratories, but in nature. Materials designed to last decades escaped into environments that evolved to handle decay. Rivers carried fragments downstream. Air carried particles invisibly. Living systems encountered molecules they had never seen before. Inside organisms, these materials behaved unpredictably. They accumulated. They interacted with cells. They triggered responses science struggled to measure. Chemists could explain how the bonds formed, but not how life would respond over generations. Attempts to reverse the reaction failed. Breaking those bonds required extreme energy, heat that destroyed everything else first. Chemicals too harsh for practical use. The very stability that made the reaction valuable now made it dangerous. This was the paradox chemistry had created. Control without foresight, precision without restraint. The accidental reaction had become a global experiment, running continuously, with no clear endpoint. And yet, the world remained dependent. Convenience outweighed caution. Innovation outpaced regulation. The reaction continued, not because it was perfect, but because stopping it seemed impossible. Chemistry had revealed its true power, not just to create, but to commit the future to a single decision made long ago. The moment of realization came quietly, not in a single study or headline, but through accumulation, layer by layer, particle by particle. The world began to notice that the reaction never truly ended. What was once accidental had become permanent. A chemistry designed for stability now resisted every attempt at balance. Oceans carried its fragments. Soil absorbed it. Even the air held traces of bonds that refused to break. The reaction had escaped the lab and rewritten the environment itself. Chemists responded the only way they knew how, by searching for new reactions, new pathways, new ways to undo what had already been done. Some progress emerged. Materials that degraded faster, bonds that weakened under light. But every solution revealed another trade-off, another compromise. This is the true climax of modern chemistry. Not a single discovery, but a reckoning. The realization that every reaction carries a future with it, that creating something new also creates responsibility, and that even small mistakes, repeated billions of times, can reshape a planet. Today, chemistry stands at a crossroads. It still fuels medicine, energy, and innovation, but it now carries a deeper question. Not what we can create, but what we should allow to last. The accidental reaction taught us that power without foresight leaves echoes that never fade. Understanding chemistry is no longer optional. It is the language of the modern world. The choices we make at the molecular level quietly decide the shape of tomorrow. And once a reaction begins, history shows us it rarely stops cleanly. Subscribe to join the journey.